Good afternoon. It's great to be here, and I would say it has been a really excellent meeting, and I've learnt a lot, even in my very compromised state of mind. So I'm going to talk about evaluating damage functions for wooden furniture, and damage functions is maybe not the correct term. Maybe the better term is damage predictions or damage warnings. And I work for English Heritage. We're charged with caring just over 1 million objects spread over 130 sites across England. And one of the tools that my colleagues use is a decennial audit. And this generates essentially a work plan for the next 10 years. It's combined condition audit and risk assessment. And it generates a lot of information, but one of the interesting pieces of information it generates for myself are the materials that have been most damaged in the last 10 years, those that have scored 3 or 4 on the audit. And this slide is running those materials in that order from your left to right. So the most damaged material is archaeological iron. And if you dig into the data, you'll see that's archaeological iron in storage. And the last audit, it was archaeological iron on display. And we've done a lot of work in the 10 years to improve that. But the second material there is wood. And again, if you dig into the details of those objects, the most predominant object is wooden furniture, hence the driver to do this research. Now, we have some frankly scary environments, and quite a lot of them. We have very damp climates, we have very dry climates, although we've reduced those quite a bit, and we have climates that fluctuate a lot. And we've been mentioning BESO. Somebody mentioned test chambers. Essentially, a lot of our sites are as good a test chamber as you could ever find for organic objects. And although we can provide good climates in microenvironments, and we do in even very challenging situations like this, most of our rooms, less than 1% of them meets the BESO RH specification of 40 to 60. So we're very interested not in what are safe or low change ranges, but how the risk increases as we go outside of those ranges. And as an example, because there's been a lot of research done in the last 20 years on archaeological iron, this kind of data is really useful for us. So it tells us not what is a very low change RH, but how steeply the risk goes up as the RH increases if we can't maintain those environments. And this is the reason we've been very interested in damage functions. And we've done a lot of developing and testing damage functions. So on your left is collated data to look at 4 mold damage functions on wood that are published in the literature, and comparing that with observations of when we've seen mold. And on the right, some work to do with a damage function we developed for silver and testing it to check that it actually does work or fit in with what we're observing on the collections. Now, we have a damage database. When the conservators observe damage, we make a record. And within that, the date that they observe damage is easy to record. But what's much more difficult is the date at which we last know that damage wasn't there. What's the period that that damage occurred over? Because we only have 5 conservators, 130 sites, some of the sites they don't get to that frequently. But we have that kind of gross data, but it's very difficult to compare that with numerical damage functions because of that uncertainty when the climate potentially caused the damage. And we've been using acoustic emission, and although I didn't make Horst talk this morning, I'm afraid I didn't really feel up to it. I hope I won't repeat too much of what he said. But we've been using this for quite a lot of materials, including wood, and we've been doing it for about 20 years now. And it's in some ways an ideal technique because in the best conditions, we can detect very small microfracturing, pre-damage, not actual damage itself. And for this work, we've used equipment by Physical Acoustics. We've used two types of equipment. The Micro 2 PC is shown on the slide. The sensor is the sensor. We have a white lead going into an amplifier and then a black coaxial cable. And this cable can be 10 meters, 20 meters, 40 meters, even 150 meters long. So it gives us a convenient way of placing the sensors, and I'll explain why that setup's important to us in a second. And we've been using very sensitive WD sensors in what's called anti-correlation mode. So as we have two sensors far enough apart that they can't hear each other. If both of them go off, we assume that is noise. If just one of them goes off, we assume that is signal. And the biggest limitation with acoustic emission for using it in our thing is sorting out the noise, because you get a noise from electromagnetic radiation. A lot of our properties don't have a great deal of lighting or alarm systems or air conditioning, but there's still electromagnetic radiation there. And you certainly get noise when the public are in the space, but exactly what's causing that noise, I don't think we know. And the other thing we've been doing, because of the people being around, when we're measuring a piece of furniture, we put a triaxial shock logger on the piece of furniture as well, so as we can measure if anybody's actually trodden on the floor a bit of a distance away and it's moved, or they've actually bumped into it, which actually happens far more frequently than you would hope. We're measuring in historic environments, which gives us some challenge. We have to be able to hide the equipment. We have very few 24-hour plug sockets, so as often the power is a long way away from the object we want to measure. So in this instance, we've measured this table and this piano, and the equipment sat under here, but we could use the leads to bring the sensors across here. And having the flexibility with those long sensors does help us. The first bits of monitoring we did objects that were a little bit away from the public. So it was behind stanchions, and the equipment sat in here. We were monitoring this table here. And again, I've shown you this, but there's actually a stanchion running along here, so as the public can't get right up to those objects. But then we had to move into more populated spaces. And there are a number of advantages if you've got more than two sensors. One of the things that you can do is actually look at location by timing the time to the signals. You need very sensitive sensors for this for wood, because often the signal attenuates quite quickly. It's certainly not heterogeneous, and the numbers that you'll get out of the automated software are wrong. But we use a translation. So what we do is we put a sheet of Melanex on there with a 1 millimeter grid marked. We do pencil breaks at every 1 millimeter, see where the software thinks that's coming from, see where we know it's coming from, and then generate a matrix to correct it as such. So as we have the anti-correlation, but we also have the triangulation. If the signal's within the triangle, we think that is not noise. The other drawback with long-term monitoring with acoustic emission is you need the sensors to be in close contact to the object, and whatever system you use, they can come away. And normally you test this manually with a pencil break test by the sensors maybe once a week. But this is quite time consuming, and we've been doing this in sites all over the country. If you have multiple sensors, so as if we have the 3 sensors for the triangulation, we can get the software to pulse them and check the other sensors pick it up. So as we can check those 3 sensors are still coupled, and we get it to do it every day. And if we've got another sensor for the second sensor, again, we can do the same thing. And if we ever get Wi-Fi in our sites, we could then look at that remotely. But at least we can get alarms set up on the system, so as people can just go and check them once a week and not have to do the pencil break tests. And usually with acoustic emission and wooden objects, we're finding a crack that we think is active, and we put a sensor on the tip of that crack. And the distance that we can detect from is maybe 9, maybe 20 centimetres, depending on the piece of wood. And there's always been this worry that, are we actually detecting that crack opening or something else? And with the location, you can see on a particular object, 83% of the energy, which is important, came at the crack tip. And over 14 objects, 76% of the energy came over the crack tip. So it does look like that assumption is correct. If we're going to do this, we need relatively good environmental data beside where the sensor is. We've used quite high quality probes. And I should have mentioned, but in the slide previously with the room sensor is on top of one of the door sills. We're quite limited where we can put room sensors, but when we set this monitoring up, we put sensors directly beside the objects. And the black sensor, we can put that sensor on a lead as well, so as we can actually have it placed just by where the sensor is. Okay, and this is the kind of result that we get. Temperature, relative humidity trace. As I say, a little bit out of BESO as an environment. And you can see the amount of energy with the red squares where we're getting acoustic emission. And then we went to look at 22 pieces of furniture and a couple of thicker beams that we're now doing. We selected them so the parameters would fit into the HERI model. So for what we have, oak and pine and 5 millimeters, 6 millimeters, etc. And that's the number of objects that we selected there. Now, looking at wood damage functions as such, and there are a number out there, and we looked at the 3 in red, but there are others. And I'll go through those in detail. The IPI Dimensional Change Index was probably the first one and is still used by some people, despite what Emma said. There are certainly people in the UK that are still using that. The HERI website, which I'll show in a minute, does a much more complex calculation. And I've also looked at Boris Pretzel's Climate Notebook, which is a toolbox, which is signal processing and something that's based in Excel. But there are others out there, but these are the 3 we chose to look at with that data set for 22 pieces of wooden furniture, each measured for 14 months to give us data either side. And this is the equations behind the Dimensional Change Index, the first set for EMC from the one of the wood books by the US Forestry Commission, and they acknowledge that this is, a single match for an isotherm. Different species of woods have different isotherms. Within a species of wood, different samples have quite different isotherms, and indeed, IPI are quite clear. This is an indication. It's not supposed to be a, really hard, fast piece of modelling. And there are issues to do with how the water moves into the wood, etc. This is what the old-fashioned software looks like, not the web version. So we have our relative humidity and our dimensional change, and we put on a value for when we think damage may occur. And there's an equilibrium time in there that you average the whole thing over. The default is 30 days, which works well for books. We've used 3 days and sometimes 5 days for these objects, related to some measurements we have on the response time of similar thickness as pieces of wood. Okay, and as I said, these are the limitations that are quite clear and shown for that model. Okay, Climate Toolbox, it's Excel-based. It's got a lot of metrics and damage functions in there. It's got some data cleaning tools, which are really useful because often climate data is not complete. And the important part for us, which I believe is based on work by Stefan, is we have a long period rolling average RH, which delineates a safe range, and we superimpose the shorter period rolling average on top of that, And if the lines cross, then that's called an RH event. And the duration and how far they're moving over delimits the severity. I would say this approach is quite similar to the European standard in some ways. Okay, and that's what the results look like. So this is our long-term average, and this is our short-term average. And where they meet or cross, that's the point that you're getting an RH event. And then finally, heavy, which I guess a lot of you attended the workshop or know this, but this is the constrained wood, and we have a number of parameters, wood species, cut, panel thickness, what we do with the means, and whether water vapor is going through one face or both. And as I say, we selected the objects as they fit within the heavy range of materials. And this is our relative humidity, and this is the calculated strain and limits that you can set on there. And essentially what we were doing was seeing if when we got an acoustic emission event, we had a prediction. So as this line went outside of this line, or the happened with Climate Toolbox, or with the dimensional change index. And these are the sort of raw results for individual pieces of furniture. This card table, and IPI predicted 67 of the observed acoustic emission events. Climate Toolbox, almost 90, performing very well there, and heavy slightly better at 96. And you can see different objects had slightly different results. And if we average for 22 pieces of furniture, we get quite a consistent trend, and the heavy does seem to be doing a better job of that. We also looked at where we had predicted instances, but there was no acoustic emission, and we set that to the same percentage compared to the damaging events just for consistency. IPI, there was none of that. Climate Toolbox seemed to have quite a high percentage, heavy a small percentage. Okay. And then in my abstract, I talked about sensitivity analysis. And what we've done previously is take our RH data and add 3% to it or 5% to it to see how that translates through in the models. But not so far before this. I thought maybe there's a better way of doing this. And if we look at the measured response of what was quite a common RH probe, Vaisala Humicap, as they're new, it's beautiful and linear, and it really does fit well with a straight line. As they start to age, it begins to drop off at the top end, and after 6 years, we're getting quite a bit of change in that. So as it's linear down here, and then somewhere about 45%, it's beginning to diverge and drop below. And what we did was actually take our measured relative humidity data, put this against it to recalculate it as if this 6-year-old probe had been used, and then do the same calculations. And many of them, it didn't make a lot of difference. They weren't massively sensitive, but 3 objects it did. So, and these are them. So this is the original reading, and this is where that recalculated data generally lowered the agreement between the predictions, as it appeared to be a more benign environment than actually it was. And I suppose, takes a while, to conclude, this is probably the best slide. And, you know, the question is, how much of an agreement do we need? 91% is pretty good. Is it good enough for what we're doing? Because we've seen over these days, there are certainly ways of improving these models if we put a lot of work in. But if we increase this to 93, 94%, is it going to make it a lot better than it is? And with the functions that are readily available to most users, all of these functions, you can put your own temperature and humidity data in, it would appear that the heavy restrained wood is the most, has had the most correlation with the observed damage on acoustic emission. I wasn't sure about my timing, so I thought I could finish there if need be. I should finish with some acknowledgements. Boris Pretzel for very kindly sharing Climate Toolbox, and if anybody's interested, he's very happy to send you a version of that. Many people who have shared their expertise in acoustic emission, and I'd very strongly agree with Hurst that this is something that you need quite a bit of experience to get good results out of. And if you're lucky enough to have people who have done it and are happy to share, that really does speed it up. And it's been a 20-year learning curve for me. A number of our conservators who have done the on-site checks weekly, which is not to be underestimated how much work that is and how important it is to keep the systems going. And much of the equipment here was purchased through a grant from UKRI's World Class Lab Fund through a scheme called CAPCO. Thank you.
Thank you, Bill. Is there any question to David?
I might move forward to here.
So my question is, when you have a piano and your sensors can only measure, you said 6 centimeters to 9 centimeters, unless you know where the crack is, you're gonna have to put like 100 of these sensors on this piano. How do you deal with that?
Yeah, absolutely. And industrially, they do put hundreds and even thousands of sensors onto things. We only have so many. We've got about 75 sensors now, and we have done a single piece of furniture with 75 sensors on it. But most of it has relied on the conservators' experience and pointing out this is the crack that we are really concerned about. But yeah, it's an expensive technique to monitor quite a small piece of wood. Things like metal and stone, the distance is much, much bigger. You can do larger structures with small numbers of sensors. But yeah, with wood, that is certainly something to bear in mind.
Thank you, David. Again, you're incredibly impressive and resourceful and practical, and I really appreciate your work. It's really valuable. I understand that the acoustic emission is very, very sensitive to very small damages, great advantage. So could you give us some kind of a sense of how much damage is associated with these events and how much cracks are lengthening, etc.?
Yeah, sure. I mean, you can, and we have, and Marcin in Lukasz's group has done calibrations against pieces of wood where you pull them apart, measure the crack, and measure the amount of acoustic emission. It gets a little bit more complex in furniture where you might have 2 or 3 different pieces of wood together and you're not sure where the cracking is. So you can relate the energy to an increase in crack area, surface area, and the values I showed you on the graph would probably relate to about 0.05 to 0.1 millimeter if the crack was going through the full depth of that piece of wood on the thing. So it is very slow. The only example I've got where we can relate this to a visual thing is we did this similar work with pieces of ivory, and we had 2 showcases. One was working well, one wasn't in terms of environment. We detected acoustic emission on the one that wasn't working well. It took us quite a while to improve things, and in 10 years we then saw a crack on the ivory object that had not been there before. So it gave us a warning of 10 years in that instance. But it is possible to calibrate it up as increasing crack distance. And then if you assume it is a single crack going through the whole depth of the object, you can then say, this is so many millimeters per year, per 10 years.
Short question and short answer.
The first graph you showed where you showed the reasons why things crack. I was just wondering if you, I was surprised at how you correlate that with humidity necessarily. Or,
Yeah.
Yeah.
Okay. And it's a very good question. So the first thing with the audit is they are trying to assess damage that's happened in the last 10 years. And we all know how difficult that is. And then when they see a particular type of damage, there's a drop-down menu of different types of damage. It might be cracking in wood. Yeah, well, there we are. Then they have to assign a reason to it, relative humidity, etc. And you can see for archaeological iron, the humidity is by far the main thing. For wood, it's quite high, but dirt is quite high as well. So I say they're indications. And I'm not knocking our conservators. It's an incredibly difficult thing to do. And we all know that many damage is a combination of 3 or 4 factors happening at the same time. But it gives us some general overview, and they're linked into solutions as well.
Very useful. Thank you.
Thank you so much, David.
Thank you.